Good day, everyone. This is Bill Stubbs, back with the sixth video in my series, Dissecting the Standard Model of Particle Physics. This one, The Secret Life of Electrons. In this video, I continue discussing the contents of my book, Three Quarks Missed the Mark, by showing that there are two types of electrons, one we know of and one hidden in plain sight, and that the electron we know of is not a fundamental particle. Let's begin. In the Standard Model, leptons, the electron, the muon, the tau, and their neutrinos are considered fundamental particles. This, even though two of the three major leptons, the muon and the tau, decay into a collection of lesser particles. Both the muon and the tau can decay into its neutrino or antineutrino, a like-charged electron, and the electron's neutrino or antineutrino. The Standard Model depicts these decays as the lepton emitting a W boson to become its neutrino, then the W boson decaying into the electron or positron and its neutrino. The problem with this is that the muon, for example, that has a mass of about 106 MeV, somehow transitions into a muon neutrino with a mass of less than 190 keV and an 80 GeV W boson. Then, the 80 GeV W boson decays into an electron with a mass of about half an MeV and an electron antineutrino thought to have a mass of no more than 2 eV. So much for conservation of energy. Welcome to the world of magic. However, as we saw in the last video, if pions are made of 136 electron-positron pairs and a valence electron or positron, muons appear to form when 33 of those pairs annihilate. This leaves 103 electron-positron pairs and the valence electron or positron in an energized pion remnant. Then, engulfed in the annihilation energy, the valence particle causes a muon-neutrino-antineutrino pair to form, creating a muon with an extra muon neutrino or antineutrino in it, a dirty muon. A dirty positive muon captures the antineutrino and ejects the neutrino to become a positive muon, while a dirty negative muon captures the neutrino and ejects the antineutrino to become a negative muon. Then, the muon decays into an electron and two neutrinos. After the muon forms, apparently the electron-positron pairs left over from the pion continue to annihilate. They do so until only the valence electron or positron and the captured neutrino or antineutrino from the pion decay remain. Then, an electron neutrino or antineutrino appears in addition to those two particles. This apparently causes the muon to decay into three particles: a muon neutrino, an electron, and an electron antineutrino for a negative muon, or a muon antineutrino, a positron, and an electron neutrino for a positive muon. So, where did the electron neutrino or antineutrino come from? Is this more particle physics magic? When the muon decays into an electron antineutrino is also emitted. Where does this antineutrino come from? Considering how the muon formed, most likely from a pair production similar to the one that created the muon neutrino-antineutrino pair during the pion decay. As is the case with the pion, after 33 of its electron-positron pairs have annihilated, after the muon's 103 electron-positron pairs annihilate, the valence electron or positron is in the presence of a large amount of energy. This pairing of annihilation energy and valence particle is apparently the recipe for creating neutrino-antineutrino pairs. An electron-neutrino-antineutrino pair forms that forces the muon neutrino out. However, when the muon decays, only its neutrino and an electron neutrino or antineutrino appears. What happens to the electron neutrinos or antineutrinos partner? Again, we can look to muon formation from pion decay for the answer. When the muon forms, only one neutrino from the pair production appears because the electrons and positrons left over from the pion decay captured the other to form the muon. It is likely that the missing electron neutrino paired with the valence electron or positron left over from the muon decay to form the free electron observed from the decay. This suggests that the free electron or positron is the valence electron or positron from the muon coupled with either the electron neutrino or antineutrino. The free electron is made of components. This means that the electrons and positrons making up the muon and the pion are different from free electrons and free positrons we see in nature. We can call them beta electrons and beta positrons after the beta particles emitted by some radioactive nuclei. Therefore, a free electron is a beta electron coupled with a neutrino, and a free positron is a beta positron coupled with an antineutrino. Now, the free electron takes on a structure similar to its cousin, the muon. It is a valence electron or positron coupled with a neutrino or antineutrino. However, unlike the muon and the pion, there are no electron-positron pairs within the free electron or free positron to annihilate and cause them to decay. Consequently, the free electron and free positron are stable particles. If it could decay, the Feynman diagram might look like this. This is likely what happens to a free electron during electron capture beta decay. For example, when 7 beryllium captures a free electron to become 7 lithium. As the Coulomb attraction between the 7 beryllium nucleus and the free electron draws the electron into the 7 beryllium nucleus, the beta electron and the electron neutrino forming the free electron separate. The free electron essentially decays. The beta electron is pulled into one of the positively charged nucleons, where it collides with a beta positron and annihilates it, which triggers the annihilation of 15 beta electron-positron pairs within the nucleon. This reduces the mass of the nucleus by about 15.8 MeV and makes the nucleon neutral, leaving the nucleus with only 3 positively charged nucleons, making it lithium. The electron neutrino from the free electron flies off as a decay product. If the free electron is a beta electron coupled with an electron neutrino, then how do the two particles configure themselves to form the free electron? The key to answering this comes from a surprising place, the electron magnetic moment. The Bohr magneton approximates the electron magnetic moment. The dimensions of magnetic moment, joules per Tesla, can be reduced to coulombs meters squared per second. In the macroscopic world, this is interpreted as the product of a current, coulombs per second, and the area of the loop, meters squared, the current is moving through. However, for a spinning particle, it seems more appropriate to interpret it as a moment of charge, coulombs meters squared, similar to the moment of inertia for mass, kilograms meters squared, times a frequency of rotation, reciprocal seconds. If I sub q is the moment of charge and nu the frequency, then the magnetic moment mu sub p of a charged particle becomes mu sub p equals I sub q times nu. The moment of inertia I sub m of a solid sphere is 2/5 its mass m times its radius r squared, and of a hollow sphere, 2/3 mr squared. Replacing the sphere's mass with its charge, q, makes the moment of charge of a solid sphere 2/5 qr squared, and of a hollow sphere 2/3 qr squared. The electron classical radius is 2.8 Fermi, about 3 times the proton's 0.85 Fermi radius, but the proton's mass is about 1,800 times that of the electron. If the density of matter making up the two is the same, then the free electron cannot be solid. To retain the matter density and the free electron radius, it must be a thin-shell hollow sphere. We know that 1,800 beta electrons fit inside the volume of a proton, so the beta electron radius is much smaller than the free electron radius. One way to get a hollow sphere with the beta electron and the neutrino is to place the neutrino at the center of the free electron and put the beta electron in a high-frequency orbit around it. If the beta electron orbit precesses about an axis through the center of the neutrino at a high enough frequency, it will approximate a thin shell hollow sphere. This beta electron hollow sphere approximation produces a free electron moment of charge of 2/3 q sub e r sub e squared, which, when multiplied by the particle's frequency nu, gives the Bohr magneton as the electron magnetic moment. So, using the Bohr magneton, we found that the free electron appears to be a charged hollow sphere created by a beta electron orbiting a neutrino. However, the Bohr magneton is only an approximation of the electron magnetic moment. Can this free electron model produce the actual electron magnetic moment? The electron magnetic moment from the Dirac equation of an electron in an electromagnetic field has a gyromagnetic ratio, or G factor, for the electron, G equals 2, which gives the Bohr magneton. However, the Bohr magneton only approximates the electron magnetic moment. Its actual value is 1.0011596 times the Bohr magneton. This small difference is thought to be additional magnetic moment components caused by quantum loop effects that add 0.0023193 to the electron's G factor of 2 from the Dirac equation. The difference, called the anomalous magnetic moment, A, is 1/2 the difference of a particle's G factor and the Dirac G factor of 2. The electron G factor is G sub E equals 2.0023193. Therefore, its anomalous magnetic moment, A sub E, is 0.0011596. This A sub E is the piece needed to determine the structure of the free electron. The Dirac G factor of 2 produces the Bohr magneton as the electron magnetic moment, which corresponds to the thin shell sphere approximation of the electron moment of charge. To get the actual magnetic moment, we must calculate the moment of charge of the beta electron orbiting the neutrino, not the hollow sphere it approximates. To do this, we use the parallel axis theorem. The parallel axis theorem states that the total moment of inertia of a body with respect to an axis not through the body, I prime, is the moment of inertia of the body plus its mass times the average distance squared it is from the axis. Therefore, the total moment of charge of the body would be the moment of charge of the body plus its charge times its average distance squared from the axis. Assuming the beta electron is a solid sphere, its moment of charge is I sub beta equals 2/5 q sub beta r sub beta squared. If it is in a circular orbit with a radius r about the neutrino as shown, its average distance squared from the axis through the neutrino is 2/3 r sub e squared. Therefore, since q sub beta equals q sub e, the moment of charge of the free electron becomes I sub e prime equals 2/5 q sub beta r sub beta squared plus 2/3 q sub beta r sub e squared, and its magnetic moment I sub e prime times nu. This moment of charge is the quantity 3/5 r sub beta squared over r sub e squared plus 1 times 2/3 q sub e r sub e squared. The moment of charge of the beta electron corrects the Bohr magneton to the electron magnetic moment. Since 2/3 q sub e r sub e squared nu is the hollow sphere approximation, which is the Bohr magneton, 3/5 r sub beta squared over r sub e squared plus 1 is the 1.0011596 Bohr magneton correction. Therefore, the anomalous magnetic moment for the electron becomes A sub E equals 3/5 r sub beta squared over r sub e squared, or 0.0011596 equals 3/5 r sub beta squared over r sub e squared, which makes r sub e equal 22.75 r sub beta. The radius of the free electron is 22.75 times the radius of the beta electron. So, the free electron appears to be the beta electron found in the pion and muon in a high-frequency orbit around a central neutrino with an orbital radius about 23 times its radius. In the next video, I will show how this free electron model can be used to get models of the muon, pion, and kaon.